Forces and fields, two new concepts, very important concepts in physics. What comes first, the field or the force? I think, this is just me here talking, I think this is something like a cause. A field, an electric field or an electromagnetic field or a gravitational field causes a force to manifest. So I could say that the effect of a field is a force. But then when I think of what is a force causes an acceleration. So in a way, a field is what causes an acceleration. It could be the acceleration of a charge, it could be the acceleration of an apple, anything that falls inside a gravitational field. So there are basically two types of forces that we're going to discuss today. Gravitational forces and electric forces. One is associated with mass and the other one is associated with charge, right? Both are surrounded by space. And both create an effect in space-time. Mass creates an effect in space-time. Mass curves space-time. So it creates a field in space-time. So this is what we're going to look today. And maybe revise the concept of work as a retrieval practice. Or maybe before we start, reflect on the concept of capacitance. Capacitance is the ability to absorb, retain, and release. So let us absorb, retain, and release air. Take a long, deep inhalation. Hold. Exhale. So that is capacitance, just to remind. Okay. So what are the differences between, or the similarities, what are the analogies between gravitational and electric field? Okay, so we said that a gravitational field happens around a mass, an electric field happens around a charge, right? But they both imply some invisible lines. We call these lines field lines. For instance, these are the field lines that we can actually visualize around a charge. This is in 3 dimensions, right? Imagine the field lines coming out in all dimensions. We call this the electric field. Definition of electric fields is force per unit charge. So the unit is newtons per coulomb, right? Now, the gravitational field, instead of repelling test positive charge in this direction, this would be the force that manifests here. The gravitational field is always attractive. It can only accelerate towards the center of the Earth. It cannot repel matter. It attracts matter. So these are radial lines. These are radial lines going towards the center of the Earth, right? And they always carry an arrow. And one of the different things is that we call the electric field E, and we measure it in newtons per coulomb. And the gravitational field, we call it G for gravity. So the unit is newtons, force, per mass, per kilogram. Definition is, again, force per unit mass. So if you put a test mass, a unit mass here, like 1 kilogram here, on this field, it will experience a force. And that force will accelerate in this direction. Right? So these are the two forces that manifest. One is of a different nature from the other, but they have similar laws, as we will see. The laws that quantify these forces are quite similar. So we'll go to the matrix. Something moves in a system, so we're talking here of a charge. Here we're talking of an apple. a mass. Charge. All right? When we think of charges, we think of electrons. When we think of mass, we think about apples, planets, anything that has matter. So this is the new matrix, right? Something moves because something pushes, and we know what pushes. The potential difference pushes. So it could be defined mathematically as energy per unit charge or energy per unit mass. Potential difference is what pushes. That means the energy per unit mass or the energy per unit charge. Right? So this is what we call the electromotive force of the voltage. Yes, the voltage creates, the difference of voltage creates a field. When there is more potential on one side, there is more positive charge, so it creates a field. And that field, that electric field, is pushing electric charges, could be positive charges. This is what we use normally is the idea of a positive charge moving from high potential to low potential. And the same thing is happening with masses. A mass falls because of a difference of potential. What is potential? What is gravitational potential difference? It is the energy per unit mass. That is the definition of gravitational potential. Energy per unit mass. Okay, and they move from high to low potential. So we could define work, but I'm going to skip work for now. I'm not going to get you confused with work. So we have fields, therefore, that will cause forces to manifest. I said at the beginning, a field causes a force, and a force causes an acceleration. So this is what explains the nature of motion. Everything in the universe is accelerating. Nothing is still. Nothing is moving in straight line in all directions. Everything is spinning fast around the center of mass or falling into some center of mass. Even falling into black holes in space-time. That is happening in the universe. So the space is very curvy, shaky and curvy. So what is the force, what units, and what formulas? What is interesting here is that force in electrics field is proportional to the charges that create these fields, inversely proportional to the distance squared. It's an inverse squared law, and that constant of proportionality is called Coulomb's constant. So force is proportional to something over the distance squared, and this number here depends on the charge. More charge, more force. Same thing here, mass and weight. Yeah, a force is a mass that accelerates, right? But if we look at the force between, for example, two planets, let's show a drawing here. A force between two planets. The force that appears on both planets is called the. So you notice that the force only appear in pairs, whether repulsive or attractive. Forces never come alone in nature. It's called action and reaction. It's a principle of nature. For every action, there is an equal and opposite reaction. So this could be the Earth, this could be the Moon, this could be the tides, this could be the face of the Moon always looking at us. These forces are there, creating tides and making the Moon look at us always with the same face, right? So these are the pairs of forces, and they are proportional to the masses. Very similar law, proportional to the masses, and inversely proportional to the square radius. So the constant of proportionality is a universal law. So very similar forces with different constants. This constant is very weak compared to this one. This was a very much stronger force. Mind you, nature has only these two forces. For example, this explains matter and everything, the motion of planets, of stars. This explains certain aspects of nature with one law, gravity, right? And this explains how we see the interactions between electrons and photons, the movement of electrons, movement of charge due to electrical forces is another force of nature. So there are two forces in nature, and then there is a third force in nature that could be subdivided into two other, like strong nuclear and weak nuclear forces. But these forces are inside the atom, nuclear forces. Outside the atom, we only have these forces. So it's like a holy trinity of forces. The ones inside the atoms, which we are beginning to understand now. The ones outside the atoms, for which we have good models. That's all we have, good models. Okay. So force and field, here goes the drawings that I just made, all the explanations. I am adding work, but okay, so again, pause the video, ponder about, what is a force, what is a field, what forces are there in nature. Ponder about the big questions in science. And then complete this map. Force, field, work, okay. It could be for revision. You need to know it. But at the end, it's about what moves and what pushes. It's about what moves and what pushes. And then we come and discover that nature makes sense. This, to me, is another big